Chapter 16, Quantum Rotation. Section 16.4, Angular Momentum and its z-component of three-dimensional rotation. The three-dimensional rotational energy of this wave function of a two-particle system is L times L plus 1 times h bar squared over 2I. I is the moment of inertia. L is the angular momentum quantum number. L can be 1, 2, 3, 4, 5. L can also be 0. In that case, the rotational energy is 0. M sub L can be from negative L to positive L. So it's possible for us to observe a degeneracy of 2L plus 1. The total rotational energy can be expressed as this. What about the rotational energy in the z direction? The expression is a little simpler. It's m sub L squared h bar squared over 2I. Again, m sub L is from negative L to positive L. So you can see the rotational energy in the z direction is always smaller than the total rotational energy here. The maximum value for m sub L is just L. You plug it in, you get L squared h bar squared over 2I, and over here you have L times L plus 1 h bar squared over 2I. The angular momentum in the z direction is simply m sub L h bar. Now we look at one specific example. This function y with L equals 1, m sub L equals 0. Well, it corresponds to the pz atomic orbital. The function is cosine theta. We'll just prove this. We'll apply the rotational energy operator to the wave function and see if we can get h bar squared over I times the wave function. The rotational energy operator is fairly complex. It's this. We're going to just apply this whole thing to this cosine theta function. Don't worry about this normalization factor. It will just appear in every single step, including at the end. Cosine theta does not depend on phi. So when you apply this operator to cosine theta, you get 0. We apply this delta over delta theta to cosine theta, we get negative sine theta. Negative sine theta times sine theta, we get negative sine theta squared. Alright? We copy this constant over here. We copy negative h bar squared over I over here. We copy 1 over sine theta here and another operator here. Now we take the derivative of sine theta squared. That's just 2 sine theta cosine theta. This negative sign and this negative sign cancel, so we have a positive expression over here. Sine theta and this sine theta on the bottom cancel, so we got this expression. And note that this is simply the wave function over here. So when we apply the rotational energy operator to this wave function, we get a constant times this wave function. That constant is the eigenvalue of this function. The eigenvalue is h bar squared over I. There's a physical meaning of this eigenvalue. It's the rotational energy of a 2pz electron. It's h bar squared over I. I is the moment of inertia of this rotating particle. Given this wave function, we can compute the rotational energy in an easier way. We'll just use this formula here. This formula comes from solving the Schrödinger equation. If we use this formula, we can just plug in L equals 1. Immediately we get h bar squared over I. That's the rotational energy of this system. The magnitude of the angular momentum is the square root of L times L plus 1 and then times h bar. In this case, L is 1. So the magnitude of the angular momentum of this wave function is square root of 2 times h bar. So over here you can imagine that on top we have the angular momentum squared. The angular momentum squared over 2I is the rotational energy. So what about the z component? Well, the z component is simply m sub L h bar. In this case, m sub L is 0, so the z component is 0. And this square root of 2 times h bar comes from the x direction and y direction. Now let's look at two other solutions over here. L is 1. M sub L can be plus 1 or minus 1. What is its rotational energy? We can again use this equation, very simple. L is 1, so the rotational energy is h bar squared over I. The magnitude of the angular momentum is again the square root of 2 h bar. Because again the rotational energy over here is the angular momentum squared over 2I. What about the z component? Well, the z component is plus minus h bar, because the z component of the angular momentum is m sub L h bar. So now we have examined three different solutions. When L is 0, m sub L can be 0 or plus minus 1. We're going to look at this graph that shows us the angular momentum vectors, and they all have the same length, square root of 2 times h bar. So over here, we know that. But they have different z component. Their z components are 0, minus h bar, plus h bar. They correspond to m sub L being 0, minus 1, or plus 1. Now, what if L is 2 or 3 or 4? Then the degeneracy becomes 5, 7, and 9. The magnitude of the angular momentum when L is 2, we'll still use this equation, okay, and also this equation to calculate the rotational energy and the magnitude of the angular momentum. Alright, so we just plug in L equals 2. The angular momentum is square root of 6 h bar. When L is 3, the angular momentum is square root of 12 h bar. What about the rotation energy? Well, again, just plug in L equals 2 here. 2 times 3 times h bar squared over 2I. When L is 3, you plug in 3 here. 3 times 4 times h bar squared over 2I. And that's the rotational energy. Again, we have two equations. One for the three-dimensional rotation energy, L times L plus 1 times h bar squared over 2I. The other is the equation for the angular momentum. Its magnitude is the square root of L times L plus 1 h bar. So we can make a lot of predictions already given the value of L for a electron, for example, in the hydrogen atom. Again, if we have a solution like this, L is 2, we plug in the number, the rotation energy is 3 times h bar squared over I. M sub L can be minus 2, minus 1, 0, 1, 2. We have a degeneracy of 5. So we have this 5 different options. They share the same energy, or specifically, they have the same rotational energy. The magnitude of the angular momentum, again, we just use this equation. It's square root of 6 times h bar. The z component is m sub l times h bar. Therefore, the value can be 0 plus minus h bar or plus minus 2h bar. When m sub l is 0, the particle does not rotate about the z-axis. Therefore, its rotational energy is distributed to x and y-axis only. And in summary, the magnitude of the angular momentum is this: the square root of L times L plus 1 h bar. Its z component is m sub L times h bar. This two can be determined at the same time. It's just because the angular momentum operator and the z component operator commute. The commutator is 0. They do commute. It's possible to determine both values exactly at the same time. Again, the degeneracy for L equals 2 is 5. The equation for degeneracy is 2L plus 1. And that's why there's 1 s orbital, 3 degenerate p orbitals, 5 degenerate d orbitals, 7 degenerate f orbitals. We can have 9 g orbitals and 11 h orbitals. If we're talking about the rotation of the electrons in an atom. But if you're considering the rotation of molecules, although we solve the same equation, we get the same solution, we have same interpretation, but instead of L, we use J as the quantum number for the angular momentum. And the z component is m sub j instead of m sub L. It's just the notation. When you see L and m sub L, we're talking about the rotation of electrons about the nucleus. When you see quantum numbers j and m sub j, that usually are used for the quantum rotation of molecules about the center of mass of the molecule. For example, if we're looking at the rotation of HCl, its rotational energy is J times J plus 1 times h bar squared over 2I. Well, J can be 0, 1, 2, 3, 4, etc. This I is the moment of inertia of the HCl molecule. Over here, it's just a simple diagram that shows you when L is 2, we can have 5 different degeneracies. Sorry about the typo here. The subscript should be 2. So this should be 2, this should be 2, this should be 2, this should be 2, this should be 2. The superscript is the value of m sub L. M sub L can be from -2, -1, 0, 1, and 2. If you look at the length of each vector, alright, these 5 vectors, they share the same length. The length is the square root of 6 times h bar. The physical meaning of this is the magnitude of the 3-dimensional angular momentum. And now you look at the 5 factors here, they have different z components. You have 2h bar, 1h bar, 0, negative 1h bar, and negative 2h bar. They correspond to m sub L being -2, -1, 0, 1, 2. So 5 vectors, same angular momentum, same rotational energy, with a degeneracy of 5. But they do have different z components. That means this 5 vectors correspond to 5 different values of m sub L.